All right, we're going to move on now to example number 5 and try to get a sense of how we can actually start to determine an nth Taylor polynomial. In the example above, we looked at a polynomial of degree 0, degree 1, degree 2, and degree 3, but how would I determine a polynomial with degree n? Well, here you'll notice that I'm going to start by working with a function of 1 over x, and I want to model this function about x equals 1. So of course that means that my x0 is equal to 1. That's kind of where I'm centered at. If you want to, over on the side, you could start to think about, we know the picture of 1 over x looks something like this. And so we're going to kind of start our initial point of contact right here. That's where we're going to draw those tangent lines and those quadratics. That's where everything's going to kind of connect to. We're going to try to model this as best we can. If I wanted to start to do this, I could think again about the general form of what one of these polynomials is going to look like. So I'll start by saying we know that p sub n of x is going to look like, well, let's see, it's going to start at degree 0, it's going to go up to degree n, and I already know the formula. It's going to be take the kth derivative, plug in 1, and then divide by k factorial. And then I'm going to have my x minus my 1 to the power of k. Again, this is my formula for my coefficients sitting up here in the front, and here's just my shift for my x's being raised to new powers. So I can push everything over to be centered at 1. So the weird part is here, I'm almost actually already done. The only thing that I need to find is this f with kth derivative and a 1 plugged in. So I'll write this. We need to find kth derivative of f with 1 plugged in. Now the hard part there is that if it's a kth derivative, I don't actually know what the kth derivative of this function is. It's not like it's an e to the x function where all the derivatives are always the same. So I might have to come up here with kind of like a general formula for what this kth derivative looks like. So let's see, let's start to investigate. We know that if I do 0 derivatives of this function, I get 1 over x. If I do 1 derivative of the function, I get negative 1 over x squared. If I do 2 derivatives of the function, I get positive 2 over x third to the third. If I do 3 derivatives of this, you might be able to confirm you get negative 6 over x to the fourth. And of course, I could just keep going and going and going. But our goal is to try to figure out what would then the kth derivative of this actually look like. Well, it might be hard to see from here. I might have to write out more individual terms to see what happens. But there might be a couple things we can start to observe very, very quickly. First off, we might be able to see that no matter what derivative I'm on, I always get x's in the denominators being raised to a power. So my derivatives look like they're going to be fractions with x to a number. But I could probably guess what x or what exponent I'm going to have on each of those. And what I'd like to do is try to relate that to what derivative I'm on. Notice if I'm on derivative 3, I get power 4. Derivative 2, I get power 3. Derivative 1, I get power 2. And no derivatives, I get power 1. Could you guess then what I might want to use as my power if I was on derivative k? Well, yeah, it might seem like maybe I could use k plus 1. Now I have to consider what happens in the numerator. And there's one thing that you might notice. Some things in here are negative and others are positive, but they seem to alternate. And if I want alternating things, I might be able to do something like negative 1 raised to a power. I'm going to start with power k just to see if that works. So let's see. If I'm on derivative 0, I should get something positive. That'll work. Derivative 1 will get me a negative. Derivative 2 will bring me back positive, so on and so forth. That's great. That tackles the negative signs. But then I need to figure out what in the world could give me the numbers 1, 1, 2, 6. If I'm not sure, I might have to try to write out a couple more of these derivatives. Notice here the next derivative, I believe, comes out as 24 over x to the power of 5. Whoops. And so if I was to go ahead and try to generalize this, can you notice any pattern between those numbers and numerators of the fraction? Yeah, you might be able to tell that those are actually just factorial values, and they match the derivative. So 6 is 3 factorial, 24 is 4 factorial, 2 is 2 factorial, 1 is 1 factorial, and 1 is also 0 factorial. So this right here seems like a general formula. Of course, when we look at the red thing that we have boxed up above, we don't want to just find that derivative formula. We want to plug 1 in for x. So that means that when we do the kth derivative and we plug in 1 for x, oh, well, that just means my denominator is going to simplify down substantially. And I'm just going to be left with this. So this right here represents my awesome red piece. And now I'm ready to simplify what I have. I like what I have up above, and I can say p sub n of x is equal to a series. Starts at 0 and goes to n. In place of that red stuff, I'm going to put negative 1 to the k times my k factorial, still have the k factorial on the bottom, and my x minus 1 to the power of k. Ooh, but now I can actually see that these k factorials could cancel, and if I wanted to, I could simplify this up a bit further. I could really just write this as negative 1 to the n, x minus 1 to the k. Now, this is some complicated work here to find that particular pattern. It's not too terrible, but it can be a little bit cumbersome at times. The cool thing, though, is to always be able to go back and see if what you did actually begins to make sense. And you should be able to tell that going to your calculator and beginning to graph some stuff. We were trying to model 1 over x, and what we found is that there was a big, long polynomial that could do it. It was always negative 1, oops, sorry, I should have down here negative 1 to the power k, x minus 1 to the k. So let's actually just see what that would actually look like here. Notice if I started at k as 0, I'm going to get my first term here is just 1. My next thing should be subtracted, and that's going to be just x minus 1. My next thing should be added, and I would have x minus 1 squared. My next thing should be subtracted, and that would be x minus 1 to the third. And my next thing should be added, and that would be x minus 1 to the fourth. And if I kept doing this, and I hit the graph button, I should see that the blue thing is modeled red thing. Let's see how well we're doing so far. Yeah, I can kind of see in here it's modeling pretty well. Of course, we only went up to degree 4. It seems like if we went maybe up to a higher and higher degree, things would become more and more accurate. Okay, so that kind of wraps up this particular example, and in the next video, we'll take a final example of the section, which is example 6.